Okay, I'm going to do a video or maybe two, depending on how much I talk, just to give you a little bit more background on magnetism. We started it yesterday, but I did it really fast because I wanted you to do the lab and I wanted you to have just enough to do the lab, but now I want you to have a bit more. So just as a quick review, so any and every magnet has two regions. One would be a north pole and one would be a south pole. Okay, so even if you cut the magnet in half, it just reforms a new north and a new south, so that you can never have just a lone monopole. You can never get a north alone or a south alone. And because, or at least we haven't yet been able to do that, and because of that, there's some ramifications in our equations. Just like in electricity, opposite poles, in electricity, opposite charges attract. In magnetism, opposite poles attract. Okay, and like poles repel. But be careful. Don't try to say like the north is like the positive and the south is like the negative, or vice versa. Okay, it's not true. North is not connected to positive or negative charge. Okay. All right, and so then every magnet has a magnetic field around it. And that was what the lab was yesterday that most of you did. One of you still needs to do, and I apologize. Spoiler alert, I'm going to ruin some of the lab today. Okay, the letter for magnetic field, and don't ask me why, because I will make up a story that will not be based in truth. The letter for magnetic field is a capital B. So and it's a vector. So the letter for gravitational field was it was a small g. The letter for electric field was a capital E. Those ones seem to make sense. Letter for magnetic field, a capital B. Okay, and so just like around any charged particle, there is an electric field. Around any particle with mass, there's a gravitational field. Around any magnet, there is a magnetic field. And yesterday, you would have seen the field lines doing this. Okay? And just like other field lines in any other field, gravitational or electric, these guys can't cross. Okay? So any object is surrounded by a magnetic field, and we determine the direction of a magnetic field by the direction that a compass needle will point. Direction of compass needle. And so hopefully in the lab you discovered yesterday that the compass needle, with help from the compass needle, that the field lines flow out of the north and into the south. Okay, that's the direction of the field lines. All right, and what we said at the beginning of the lab yesterday is that really the compass needle is really just a tiny little bar magnet that's balanced on like this tiny little point. And so because it's balanced on this little point, it's free to move around. And so when you bring it close to one pole of the magnet, it will swing around so that it's attracted to that one. And if you bring it close to the other, it swings around again. Okay, so, and it's the red end that we call the point of the compass. So yesterday, for those of you that did do the lab, it's the red end that we call the needle of the compass. Okay, so outside a magnet, the field lines flow from north to south. Inside a magnet, they actually flow from south to north, because they're really just continuous, so it should make sense. They go into the south, and they go all the way along, and they come out of the north again. Okay, so they are flowing from north to south. All right. One thing I didn't mention yesterday, before that, magnetic fields are measured in Teslas. The unit for magnetic field is a Tesla. Okay, named after Tesla, who was a famous physicist that we will talk about various times in this unit. Famous physicist that his first name is Nikolai, that didn't get a lot of credit. He might have been rather eccentric. He's really the one that figured out electricity, even though Thomas Edison gets the credit for it. And when we get to that section of alternating current, direct current, I'll tell you the story of Tesla and his true love. All right, so it's measured in Teslas, and we'll be seeing a lot of that. The one other concept that I didn't mention yesterday is something that's called magnetic flux. And you'll see it now and again. It's measured in a unit of Webers. And Webers is a WB. And it really, the best description I've heard of flux, it's the number of field lines. And if you think of it as like the number of field lines passing through a surface. Okay? Oftentimes people will say that magnetic flux is kind of like the current in electricity. Okay? And if you think of it, then the number of field lines, or the Webers, per area, which would be Webers per meter squared, that is actually equal to a Tesla. Okay? So if you think of the Webers as the field lines, and then when they're passing through a surface or through an area, then you get Webers per meter squared, and that's what a Tesla is. Okay? And we'll come back when we get to our second equation. I will show you more exactly what a Tesla is, but I don't want to really ruin the surprise right now. All right, what I do want to talk about for the rest of this video, and if I'm quick, it will be only this one, but I think we'll probably end up having to do a second one, is that really all material is made up of, atoms, and all atoms have electrons, and all electrons are really little magnets. So if that's true, then one might say, well, then shouldn't all materials be magnetic? All materials aren't magnetic because it depends on how those electrons are aligned. And so we need to look for a second, or maybe a couple of minutes, at magnetic materials. And we can categorize all materials into 3 categories. And the 3 categories are really all based on how are these electrons aligned inside the material to give the material magnetic properties or not. So the first type of material is called diamagnetic. Diamagnetic, we'll say substances instead of materials. Okay? Diamagnetic substances. In these materials, and I think in chemistry you would have been drawing electrons as arrows, right? And so you can have arrows up and arrows down representing the spin of the electron. And that's what's creating the magnetic field for the electron. So in a diamagnetic substance, the magnetic fields of the electrons actually end up balancing each other out. So the magnetic fields of the electrons balance each other out. Okay? And what that means is that then the substance does not have an overall magnetic field. Not only does it not have an overall magnetic field, if these guys are placed in an external magnetic field, they will weaken it. And how about if tomorrow I give you a copy of my notes on this, okay? So that just so you can make sure you get everything. So if anything that's a diamagnetic substance is placed in an external magnetic field, it will actually weaken the field. What I mean by an external magnetic field is, just imagine I have a magnet here and a magnet here, and so I have this magnetic field between them, and then I take some material and I place it in here. If I measured the field before I placed it in there, and I measured the field after I placed it in there, the field would be weaker when it was placed in there. As well, if I take a diamagnetic substance and I place it near a pole of a magnet, it will experience a repulsion. They will be weakly repelled.